Download this code from codegive.com, link in the description below. OK, let's dive deep into the fascinating world of LLM interpretability, demystifying the black box and exploring techniques to understand what's happening inside these powerful models. This will be a comprehensive tutorial, drawing on concepts from Lecture 24 and expanding on practical code examples. LLM interpretability, demystifying the black box. Introduction. Large language models, LLMs, like GPT-3, llama, and llama have demonstrated remarkable capabilities in generating text, answering questions, translating languages, and even writing code. However, a major challenge with these models is their lack of interpretability. We can often see what they do, the output, but understanding why they do it, the internal reasoning, remains difficult. This is what leads to the black box perception. Why is interpretability important? Trust and reliability. If we don't understand how a model arrives at its decisions, it's hard to trust those decisions, especially in critical applications like healthcare, finance, or law. Debugging and improvement. Interpretability helps us identify biases, errors, and weaknesses in the model. This allows us to improve the model's performance and fairness. Safety. Understanding how a model might generate harmful or misleading content is crucial for mitigating potential risks. Scientific discovery. Analyzing the internal representations of LLMs can provide insights into language, knowledge, and reasoning itself. Accountability. When models are used to make decisions that affect people's lives, understanding the basis of those decisions is essential for accountability. Key concepts. Before we dive into specific techniques, let's define some key concepts. Interpretability. The degree to which a human can understand the cause of a decision. A highly interpretable model makes its decisions in a way that's easy for humans to follow. Explainability. Often used interchangeably with interpretability, but sometimes refers to providing explanations for specific predictions. Intrinsic versus post hoc interpretability. Intrinsic interpretability. Designing models that are inherently interpretable, example simple linear models, decision trees. These models have a structure that makes their reasoning transparent. LLMs are not intrinsically interpretable. Post hoc interpretability. Applying techniques to understand the behavior of a model after it has been trained, example analyzing attention weights, using probing classifiers. Most LLM interpretability research focuses on post hoc methods. Local versus global interpretability. Local interpretability. Understanding why a model made a specific prediction for a specific input. Example, which words in the input were most important for the prediction. Global interpretability. Understanding the overall behavior and decision-making process of the model across a range of inputs. Example, what types of questions the model is good at answering, what biases it exhibits. Common techniques for LLM interpretability. Here's a breakdown of some common techniques, along with code examples where applicable, using Python and libraries like Transformers, Torch, and potentially libraries like Captum or InterpretML. 1. Attention visualization. Concept. Attention mechanisms are a core component of transformers, allowing the model to focus on different parts of the input when generating the output. By visualizing attention weights, we can see which input words the model considers most important for each output word. How it works. Examine the attention matrices produced by the transformer layers. The attention weight J represents the importance of the JTH input token when generating the ITH output token. Code example. Asterisk explanation asterisk. Asterisk we load a pre-trained model, example GPT-2, and tokenizer. Asterisk we tokenize the input text. Asterisk we pass the input through the model, setting output underscore attentions equals true to get the attention weights. Asterisk we extract the attention weights from a specific layer, example the last layer. You can experiment with different layers. Asterisk we visualize the attention weights using matplotlib. The heat map shows how much each input token contributed to the prediction of the last token. The visualizations show the attention paid by the generated word to each input word. Asterisk interpretation asterisk by looking at the heat map, you can see which input tokens were most strongly attended to by the model when generating the next word. For instance, you might see that France received high attention when predicting is. Asterisk note asterisk interpreting attention weights can be tricky. High attention does not necessarily imply causality or direct influence. It simply indicates that the model found a relationship between those tokens. 2 Attention rollout asterisk. Asterisk concept asterisk attention rollout aims to propagate attention weights across all layers of the transformer to get a more complete view of the influence of input tokens on the final output. Asterisk how it works asterisk recursively multiply attention weights from different layers to estimate the total influence of each input token. Asterisk benefit asterisk can provide a more comprehensive understanding of token importance than just looking at attention weights from a single layer. Asterisk explanation asterisk. Asterisk the code first obtains the attention weights from all the layers. Asterisk then, the attention underscore rollout function computes a global attention map representing how each input token attends to every other input token, taking into account the structure of all transformer layers. Asterisk it optionally allows for the discarding of low attention weights to improve clarity. Asterisk finally, the rolled out attention matrix is visualized to reveal the propagated dependencies between tokens. Asterisk interpretation asterisk. Asterisk the attention rollout matrix provides a more global view of token importance. The intensity of each cell represents the strength of the connection between the corresponding input tokens after propagating attention across all layers. This helps to understand the hierarchical relationships learned by the model. 3 Gradient-based methods, example input gradients, integrated gradients. Asterisk concept asterisk calculate the gradient of the model's output with respect to the input embeddings. This gradient indicates how much a small change in the input would affect the output. Areas with larger gradients are considered more important. Asterisk input gradients asterisk the most basic approach. Asterisk integrated gradients asterisk an improvement over input gradients, addressing the issue of saturation, where gradients become small even when the input is important. Integrated gradients integrate the gradients along a path from a baseline input, example all zeros, to the actual input. Asterisk libraries asterisk Captum, a PyTorch library, is commonly used for gradient-based interpretability methods. Asterisk code example, integrated gradients with Captum. Asterisk explanation asterisk. Asterisk we load a model and tokenizer. Asterisk we tokenize the input and obtain the input embeddings, the numerical representation of the tokens. Asterisk we define a predict function that takes the input embeddings and returns the model's output. Here, the output is the logits, pre-softmax scores, for the next token. Asterisk we initialize the integrated gradients object. Asterisk we define a baseline input, usually a tensor of zeros with the same shape as the input embeddings. Asterisk we call ig.attribute to calculate the integrated gradients. This computes the gradients along the path from the baseline to the input. Asterisk we sum the attributions over the embedding dimensions to get a single attribution score for each token. Asterisk we visualize the attributions using a bar chart. Asterisk interpretation asterisk the bar chart shows the attribution score for each input token. Tokens with larger attribution scores are considered more important for the model's prediction. For probing classifiers asterisk. Asterisk concept asterisk train a simple classifier, example a linear classifier, to predict a specific property or attribute from the hidden states of the LLM. Asterisk how it works asterisk. Asterisk extract the hidden states, the activations of the neurons, from one or more layers of the LLM for a set of inputs. Asterisk create a labeled dataset where the input is the hidden states and the label is the property you want to predict, example sentiment, part of speech, topic. Asterisk train the probing classifier on this dataset. Asterisk evaluate the performance of the probing classifier. Asterisk interpretation asterisk if the probing classifier can accurately predict the property from the hidden states, it suggests that the LLM has encoded information about that property in its internal representations. Asterisk benefit asterisk can reveal what kind of linguistic or semantic information is being captured at different layers of the model. Asterisk example asterisk imagine training a probing classifier to predict the sentiment of a sentence from the hidden states of a particular layer in GPT-3. If the classifier achieves high accuracy, it suggests that that layer is sensitive to sentiment. Asterisk explanation asterisk. Asterisk this code tokenizes and encodes a sample dataset of sentiment-labeled texts using the Hugging Face Transformers library. Asterisk it then retrieves the hidden states from the specified layer of a pre-trained BERT model, which represent the model's internal understanding of the input. Asterisk the hidden states corresponding to the CLS token are extracted to capture the overall sentence representation. Asterisk a logistic regression model is trained to predict the sentiment labels based on these hidden states. Asterisk the accuracy of the probe model indicates the extent to which the hidden states capture the sentiment information in the input text. Asterisk interpretation asterisk. Asterisk the accuracy of the probing classifier provides insight into how well the hidden states represent the sentiment of the input texts. Asterisk high accuracy indicates that the model encodes significant sentiment information in the hidden states, whereas low accuracy suggests that the hidden states are less informative with respect to sentiment. Asterisk this information can be used to understand the internal representations of the model and how it processes sentiment. 5 counterfactual explanations asterisk. Asterisk concept asterisk find the smallest change to the input that would flip the model's prediction. Asterisk how it works asterisk. Asterisk start with an input and its corresponding prediction. Asterisk search for a minimally modified input that results in a different prediction. This search can involve various techniques like gradient-based optimization or genetic algorithms. Asterisk interpretation asterisk the counterfactual input reveals what factors are crucial for the model's decision. Asterisk example asterisk if a model predicts that a loan application should be rejected, a counterfactual explanation would show what minimal changes to the application, example increasing income, reducing debt, would lead to approval. Asterisk challenge asterisk finding good counterfactual examples can be computationally expensive, especially for complex models like LLMs. Asterisk libraries like IX360 in Python offer tools for generating counterfactual explanations. However, adapting them to LLMs can be challenging. 6 concept activation vectors, CAVs. Asterisk concept asterisk identify directions in the model's activation space that correspond to specific human understandable concepts, example positive sentiment, masculinity. Asterisk how it works asterisk. Asterisk define a set of examples that represent the concept you're interested in, example a set of positive sentiment sentences. Pass these examples through the model and extract their activation vectors, hidden states, at a particular layer. Use these activation vectors to train a classifier, example a linear classifier, that distinguishes between examples that have the concept and examples that don't. The normal vector to the separating hyperplane of this classifier is the CAV. It represents the direction in activation space that corresponds to the concept. Interpretation You can then use the CAV to understand how the model uses the concept in its reasoning. For example, you can measure the alignment between the CAV and the activation vector of a new input to see how strongly the model is activating that concept for that input. Benefit can help reveal biases or unexpected relationships between concepts in the model's representations. Library TCAV, testing with CAV, is a library specifically designed for this technique. However, adapting it directly to LLMs requires careful consideration of the input and output formats. 7. Knowledge editing concept, modifying the model's weights to correct factual errors or update knowledge. This directly probes the model's stored facts and offers interpretability. How it works, identify the specific weights that influence the model's factual knowledge. Apply targeted updates to these weights using techniques like fine-tuning with specific examples or using specialized knowledge editing algorithms. Interpretation, by observing how specific weight changes affect the model's output, you gain insight into where and how the model stores and uses factual information. Library, libraries like Rome, Rank 1 model editing, provide tools for targeted knowledge editing in transformer models. Challenges and limitations. Complexity. LLMs are incredibly complex, and even with these techniques, it's difficult to get a complete and accurate understanding of their inner workings. Spurious correlations. Interpretability methods can sometimes highlight correlations that are not causally related to the model's decisions. Context dependence. The interpretation of a model's behavior can depend heavily on the specific input and context. Scalability. Some interpretability methods are computationally expensive and don't scale well to very large models. Adversarial examples. Interpretability methods can be fooled by adversarial examples designed to mislead them. Evaluation. It's difficult to objectively evaluate the quality of interpretability methods. How do we know if an explanation is good? Best practices. Use multiple techniques. Don't rely on just one interpretability method. Combine multiple techniques to get a more comprehensive picture. Focus on specific questions. Frame your interpretability analysis around specific questions you want to answer. Example: why is the model biased towards X? What knowledge is the model using to answer this question? Validate your findings. Test your hypotheses by modifying the model or input and observing the effect on the output. Be aware of limitations. Recognize that interpretability methods are not perfect and can be misleading. Document your analysis. Keep careful records of your interpretability analysis, including the techniques you used, your findings, and your limitations. Conclusion. LLM interpretability is an active and rapidly evolving field. While it's impossible to fully open the black box, these techniques provide valuable tools for understanding and improving these powerful models. By combining these techniques with careful analysis and validation, we can gain greater trust, reliability, and control over LLMs and harness their potential for good. The code examples provided here are starting points. Experimentation and adaptation are key to unlocking deeper insights into the behavior of your chosen LLM. Remember to always be critical and aware of the limitations of each method. Good luck on your journey to demystifying the black box.